All right, so again, we're usually not going to have quizzes, so we will still split the lecture into two parts, a part A and a part B, with about a 3-minute break to run to the restroom or get a drink of water or just stretch if you need to. Just reminding you and handing out these bookmarks to use the Math Lab. They are a place where you can go to get help. You can also, people really haven't been coming to my office hours, you can come to my office hours. You can email me questions. A few people have done that. Please let me know when you have questions and you want help with those. Lecture A, we're going to review probability, PDFs and CDFs, along with improper integrals in the context of one of our main real-life applications, and that is what are called lifetime random variables that are important for engineers and actuaries. They are variables that are supposed to model how long something will last. It could be a light bulb, it could be a machine, it could be a refrigerator. How long will the refrigerator last before it breaks down? It could be a person. How long will a person last before they break down, before they either get sick or die? That's all important for engineers and insurance companies and that kind of thing. And so we're going to get our first introduction to that kind of thing in the context of reviewing what we've been doing with probability and improper integrals. And lecture B, we're going to go back to geometry and talk about volumes by slicing again. And this time it's volumes of what are called solids of revolution, where you take a region in the plane and you rotate it or revolve it around some axis to create a solid. And we want to be able to find the volume of that solid. There's a formula you can use, but we want to understand in an intuitive way where the formula comes from when you think of it like a physicist would think of it, for example. Remind you that tomorrow, actually now, there's a presentation by a representative or two from the company Allianz, 3 to 4 o'clock in CC 230 tomorrow. Treats are going to be provided, but I need to know how many people to expect, so excuse me. If you plan to come, please let me know. If you don't plan to come, you don't have to bother sending me anything, but if you think you'd like to come, please let me know so I can get treats. Make sure everybody's got a cookie or something like that. All right, so let's review probability and so forth in the context of these lifetime random variables. Since it's an amount of time, it's common to use the letter T for lifetime random variables. Let T equal the amount of time something, a refrigerator, a person, lasts until they die, okay? So this feels a little bit morbid. So you could call this death random variables or something, but we want to be positive. We want to call it lifetime. How long will you live? The amount of time something lasts until failure. I'll put the word failure in quotes. Failure can mean a lot of things. Okay? So it's a random variable. Different people live different amounts of times. Different refrigerators last different amounts of times before they break down. Different cars do. So it's a random phenomenon. You can model it with probability. What are the chances that this person is going to live to be at least 90 years old, for example? You're going to answer that question as an insurance company to know how much, you should charge them for their premium so that you can pay their spouse when they die, for example. Give them the benefit. We want to start simple, okay? Start simple in our modeling and see if simple models work, and then you try to build up toward more complicated and perhaps more accurate models. Start simple in our modeling. That is a basic principle that you want to have. What's the simplest kind of PDF there is, for example? Turns out the simplest kind of PDF is one whose graph is horizontal. It's called a uniform distribution. So this is example 1, you might say. Where'd the eraser go? Put it over there. Example 1, I a uniform distribution. Where the PDF is a horizontal line. But it can't keep going on forever as a horizontal line, because what we know about PDFs, we know the total area under them has to be 1. So it's got to stop somewhere and go back down to 0. Let's go ahead and pick a particular number. Let's go ahead and pick 100. I'll think of this as the lifetime of a person, okay? This is going to be my f of t, little t. Capital T is going to represent the random variable. Little t is going to represent sort of like actual time. So this is the t-axis. What would this model say? This model is the density here, this probability density function is horizontal. So in a sense, any little window of time, like 1 year or even 1 month, of the same length, let's just consider 1 year at a time, a newborn baby has the same likelihood of dying at any year of their life up to age 100, is basically the idea. Their chance of dying between 20 and 21 years old is the same as their chance of dying between 98 and 99 years old. That doesn't sound too realistic, does it? But it's simple, okay? So you can try this simple model, see how good or bad it does, probably very bad, with reality, and see if it's worth using. The probability that t will be between a and b, as usual, will be the integral of the PDF from a to b. And in this case, it's just going to be the area of a rectangle. You don't even have to bother finding the antiderivative. Just find the area of that rectangle. Well, what else am I going to need if I'm going to find the area of that rectangle?
The height.
Need the height, yeah. I got the width of the whole thing, 100. Okay. There is a side of this rectangle, but it's not really part of the graph. The height, to make the total area equal to 1, would have to be 1 over 100. That would be the height. So the integral from a to b is going to be b minus a over 100. So this would say, for example, your chance of dying between your 20th birthday and your 70th birthday would be 50 over 100. 70 minus 20 is 50 over 100. That would be 1/2. A 0.5 chance that a newborn baby would die between the ages of 20 and 70. Again, it's not accurate. Could it be accurate for other situations? I don't know. Maybe in certain situations, like for light bulbs or something. How long does the light bulb last? Maybe it is more accurate. Though it wouldn't be 100 years, it'd be more like maybe 100 weeks or something. Actually, these newer light bulbs, they do have the benefit of lasting longer than old light bulbs used to. Have you noticed that? They don't seem to burn out quite as fast. So this is the PDF. And you find probabilities by integrating. What about the CDF? What does its graph look like? The CDF is going to be an antiderivative of the PDF. We said that last time. What antiderivative? Not just any old antiderivative. Its value, if this one's non-zero right at t, starting at t equals 0, its value at 0 has to be 0. Because what is the PDF? The PDF, capital F of t, is the probability that your variable is less than or equal to little t. I used x's before instead of t's. In this case, you could write down as the probability that capital T is between 0 and little t. It's the area under this graph from 0 to some unspecified number, little t. It's going to be t over 100. If I go up to some unspecified number, little t, the area of the rectangle from 0 to t for the base and a height of 1 over 100 is going to be t over 100. The formula for this is going to be t over 100. It's going to be a straight line with a slope of 1/100. It's an antiderivative of this. The derivative of that, of the CDF, has to be the PDF. It's going to be up to 1 by the time you get to 100. This newborn baby must die by their 100th birthday, okay? According to this model, they have no chance of living past their 100th birthday. The moment they hit 100, they die, if they've lived that long already. Okay? They can't make it past. You find probabilities with areas under the PDF, and you look at the values of the CDF. If you want to find the probability of being between A and B, you can think of that this way, but you can also think of it as capital F of, well, okay, this is capital F of t minus capital F of 0, but in general, the probability that t is between A and B is going to be capital F of B minus capital F of A. Just like the fundamental theorem of calculus. That's what the fundamental theorem of calculus says. This is an antiderivative. All right, what about another example? Second example. You might say, okay, let's just say, again, to keep things simple, all people have to die by their 100th birthday. But they are more likely to die, you know, newborn babies more likely to die when they're older than when they're younger. So maybe a more accurate model is a straight line model for the PDF with a positive slope. Positive slope. Making the density higher near the older ages, like that. How high should it go? There's a triangle. I want the total area still to be 1. The area of the triangle is 1/2 base times height. The base is 100. 1/2 times 100 is 50. To make the total area 1, I need to make the height 150. Twice as high on the same scale as that graph. We go up like this. So my little f of t in this case would be t over 50. That would be the formula for that one. The formula for this one would be 1 over 100 for t between 0 and 100. Technically, it's 0 otherwise. This one's t over 50, once again, for t between 0 and 100. Probability still can be found by computing areas. The probability of dying between time A and time B is the integral of this thing from A to B. Since it is a straight line, the graph, you could find those areas by finding the area of a trapezoid here, like that. But you can also integrate it. Antiderivative is going to be t squared over 100. Evaluate that from A to B. The probability of dying sometime between time A and time B is going to be b squared minus a squared over 100. Oh, I forgot something. What's that? Something bothering me about this. Is that right? Base times height. Area is 1, right? I'm still feeling like something's wrong here because when A is 0 and B is 100, that's good because of 100.
150th times the derivative of t, the derivative.
What are you saying?
Yeah, it's like it should be, so the derivative of 1/50th times the derivative of t, down right on your second to last line. Yeah, and then I think you did that wrong.
There was no half.
Well, I did that with the 100 there. I'm not seeing what's wrong with it. Something's
Why
wrong.
is f of t divided by 50? Because then at 100 wouldn't it
It'd
be
be
2?
1/25.
The equation, why is it t over 50?
That's the problem, thanks. Yeah. I want it to be at 1/50th when t is 100. I was thinking the slope was 1/50th, but the slope is now 1/50th. That was my mistake. The slope, rise over run, is going to be 1/50th divided by 100. Rise over run. So that'll be 1 over 5,000. Right? And the formula is t over 5,000. That makes this work out right. Yeah, that makes it work out right. B squared minus a squared over 10,000. That's the problem. I looked at that 150 and thought, oh, that's the slope. No. That's the rise for a run of 100. So the slope is much smaller. It's 1 over 5,000. So I was wrong. Well, no, it still goes up to 1/50th here. It still ends up being twice as high in that scale over there. Then when a is 0 and b is 100, I get 10,000 over 10,000. I get a probability of 1. What about the PDF, or the CDF, excuse me? It's the integral of the CDF. Let me use a different letter. F of w dw as w goes from 0 to t. Antiderivative is w squared over 10,000. You evaluated from 0 to t. You get t squared over 10,000. The graph of the CDF is a quadratic. It's a parabola, or a half of a parabola. Looks like that. When t is 100, it's up at 1. Once again, if you have this graph, you don't have to integrate it to find probabilities. You do subtraction. Of fundamental theorem of calculus, really. So what's the probability that somebody's going to die between the ages of, say, 60 and 80 here? You can plug 60 in for A and 80 in for B. Get 80 squared minus 60 squared over 10,000. Simplify that. 6,400 minus 3,600, that's going to be 2,800. Over 10,000, a 0.28 probability that they die between the ages of 60 and 80. On this graph, it's a difference of values. With 80s right here, 60s right here. That's 6,400. Well, 6,400 over 10,000, which is 0.64. This value is 3,600 over 10,000, 0.36. The difference is 0.28. The difference in height there, that's the probability that you want. What are the improper integrals? Well, that's for example 3. This was example 2. What about example 3? Technically speaking, people can't live to be an arbitrarily large age. So I'm going to show you the exponential model here again. So the exponential model would be a bad model for lifetimes in reality. And it's higher at lower values, and seeming to say that most people are going to die when they're young. So it's definitely not good for lifetimes of newborn babies. Could it possibly be good for lifetimes of other things, like light bulbs? Might be better than it is for people. Actually, you can use it in wait times for other things. Wait times. like how much time to wait between hurricanes. We already talked about how much time to wait between cars in the intersection, but you can also do it for between hurricanes or between earthquakes in a certain area. Actually, if you do study actuarial science, they go ahead and try to use exponential models sometimes anyway. Just because they are relatively simple. Exponential model. Now the graph goes on forever. The total area from 0 to infinity has got to be 1. Lambda e to the negative lambda t was an equation we wrote down before for the general exponential model. Integrating something like that from 0 to infinity is an improper integral. Let's go ahead and redo the calculation. I could see putting something like this on the first regular
Because we have the
example.
negative sign.
Thank you. It's a limit as b goes to infinity of integrals like this. Now I use the fundamental theorem of calculus, find an antiderivative of lambda e to the negative lambda t. You can do that with a substitution. You can also just write it down. It's negative e to the negative lambda t. You can write it down just by guessing, educated guessing. I did this calculation before. You've got to be super careful with your minus signs. That is a 1. 2 minus signs make a plus. We're really doing the limit as b goes to infinity. I could write it as 1 minus e to the negative lambda b. That goes to 0 as b goes to infinity, since lambda is assumed to be positive. So negative lambda is negative. Negative lambda is negative. So the limit is 1 minus 0 is 1. It is a PDF. Integrating it over any interval would give you the probability that t is inside that interval. And what's the corresponding CDF? Capital F of t. Again, at the sort of first non-zero value of the PDF, so to speak. Actually, it can be 0, but here it is non-zero. It's up at lambda there. When t is 0, that's sort of the initial place that capital F starts to increase. You integrate little f, in this example, from 0 to t. I'll call it little f of w dw. Same PDF, lambda e to the negative lambda t. Same antiderivative, negative e to the negative lambda t. But now the upper limit of integration is a t instead of infinity. No limits to do here. So this is supposed to be a w, sorry. What you're going to get upon simplification is 1 minus e to the negative lambda t. So the CDF has a graph that looks like this and has a horizontal asymptote of 1. It approaches 1 as t goes to infinity. Once again, areas under this graph give you probabilities. Differences, vertical distances along that graph give you probabilities. Because of the fundamental theorem of calculus. So, trying to review everything, trying to get these things solidified in your mind. Okay? You can expect probability problems where you have to integrate to find probabilities to come up in the exam. Let's also briefly talk about complications that can arise when your model is not so simple. I'll call it example 4. Maybe for some reason, your PDF I'm going to make it go out to infinity here. Maybe it's got some wobbles in it, its graph. Some sort of oscillations like that. Could that happen in real life? It's hard to say. It's certainly not real simple. And I'm not an expert in this, so I don't know for sure if something like that could happen in real life. Is it plausible? I think it might be plausible. At least maybe for, here's my imaginary plausible situation. At least for babies when you're considering babies born during a certain time of year, each year. Maybe you're in a poorer country, third world country, and you have a monsoon season or in a drought season every year. And maybe people are more likely to die during the drought seasons. And because of that, maybe it's possible you could have some wobbling in your PDF here for the lifetime. Now again, lifetimes like this probably aren't good for babies anyway. Because again, it would still imply, because it's higher over here, that most babies would die young. Most people after they're born would die young. So it's still not going to be realistic for that kind of thing. What kind of function is going to have that kind of graph? Well, you actually considered functions similar to this in homework. To get some oscillation in there, you might want to use the trig function. And to make it decay to 0, fast enough for the integral to converge, you might want to divide by like t squared. So you might have something like this. 2 plus sine t over t squared. Probably has a graph that looks like that. Let's use Mathematica now. Take a look at this. So let me go ahead and assume that's my PDF. Although it's not necessarily a PDF, right? Because the area is not necessarily 1. But let's initially see what Mathematica will do with it anyway. Mathematica, can you integrate this? If I try to do the definite integral symbol from 0 to infinity, my guess is it's going to have trouble with it. Maybe not even give an answer. It does not converge. Okay, I was expecting that to converge, though. That makes sense when Mathematica is saying it there. I think Mathematica is wrong. I think it does converge. Could Mathematica really be wrong? Let's see what n integrate produces, if anything. If it is converging, it's converging slowly. Let's try a really big number here. Well, let's try 100 first, see what happens. Wow, we are getting a very big number. I guess I'm wrong in my thinking this conversion. Why would that be wrong? See, 2 plus sine t is always going to be between 1 and 3. Right? Because sine of t is always between -1 and 1. So when you divide it by t squared, like this, that's going to be true. And the integral of this one converges. Let's just make sure that the plot looks like it satisfies that condition that I wrote up there. I'm going to graph 1 over t squared, f of t, and 3 over t squared. Our graph should always be between them. The graph we're interested in is going to be blue. It is always between them there. The blue graph is always between them. If we go out further here, you can see it better. So by the comparison, what I'm trying to get across is by the comparison test, the integral under the blue should converge. I know the problem.
Goes to infinity.
I need to start at t equals 1 if I use this. The problem is at 0. It goes to infinity there, yeah. Okay, let's put a plus 1 down below. That makes this comparison be what the comparison would be. And ultimately, when you add 1 here, that's less than or equal to 3 over t squared. The integral from 1 to infinity can be shown to converge by the comparison test. And then the integral from 0 to 1, if you add the 1 down there, you don't have to worry about it being improper. It's not improper. It is proper from 0 to 1. You know what I'm saying here? Say it again. Ultimately, you could compare this to that function when t goes from 1 to infinity, and by the comparison test, the integral of this from 1 to infinity would converge. And then the integral from 0 to 1 you don't have to worry about because it's not improper there. You're never going to divide by 0, no vertical asymptote. So Mathematica wasn't wrong. This one did diverge, but the divergence was at 0, not infinity. Let me add a 1 to it. See what happens. Okay, it didn't give up, but it gave us a strange answer. What is that answer approximately? It's approximately 3.78835, not 1. We could compare it with these things, adding a 1 to the bottom just to show you the graphs between them. Like before. But now there's no problem near 0. If we graph this from, say, 0 to 2 instead, we see there's no problem near 0, that no vertical asymptote there for any of those. Does n integrate produce this? Can I do n integrate with infinity as one of the limits? Yeah, it produces the same thing. So if I want a PDF, I should really divide that function by this number approximately. In reality, I guess I should have divided by this number. Crazy, huh? Okay, let's go ahead and do it. You know, we don't have to worry about what that crazy stuff means. All we have to do is copy and paste. How about that? I can divide by that number so I can put it in here. Like this. I'll use parentheses. Pasted. Now we have an integral that equals 1. Aha! It didn't simplify it. Simplify to 1? Come on! Oh, really? Okay. Sorry. That simplifies to 1. That's a 1. Anyway, so now we have a PDF. We can integrate it to find probabilities. Now f of t is the new function. If I integrated, for example, to from 60 to 80, and if I was using it as a lifetime model for people living, I'd estimate the probability of dying between 60 and 80 to be, oh, come on. Did it not like my copying and pasting, maybe? Oh, fine. 3.78835, but that's only an approximation. Close enough? Okay, the probability according to this model that they're going to die between the ages of 60 and 80 is less than 1%, about 1/5 of 1%. Not accurate. Okay. How are we doing on time? It's about break time. Let's go ahead and take a break. After break, we will look at a more careful proof of the comparison test, and then we'll do volumes of revolution. Take a 3-minute break.